first unit by talking about some graphing principles. The first one that we're going to talk about is the fundamental graphing principle for functions, which states that all points that we put into the equation satisfy the equation itself. So that is a specific point on the graph if and only if y is equal to the function itself. And there's a few different ways in which we can graph these. On the left here, you'll see that we have a table of values which can help us graph and specifically find some points. And then using Desmos, I also put in into Desmos this graph as well, so we can see when using Desmos, when we put our cursor and click on specific points that are highlighted within Desmos, that we get some important pieces of information. We end up finding the x-intercepts, we end up finding the y-intercept, and then we end up looking at a minimum value of our point. So it can give us a lot of information just by clicking around on the graph itself. On the second page of our notes, we want to talk about the zeros of a function. So zeros are known as the solution to the equation. In other words, x is a zero of the function if and only if it is an x-intercept. So a solution is the same language as x-intercept is the same language as zero. So if I'm looking at the graph below, a zero, x-intercept, or a solution is anywhere our graph crosses the x-axis. These are known as the real roots. We do know that there can be non-real solutions in the complex world, and we'll talk about those later. Some steps for testing if a graph is even or odd, and for seeing that if there is symmetry. So the graph is symmetric about the y-axis if and only if I substitute negative x into my function and I obtain the original function itself. It is symmetric about the origin if and only if I substitute negative x into my function and I get the opposite function itself. We call an even function when it is symmetric about the y-axis, and an odd function is symmetric about the origin. So when I'm looking at some pictures below, some example pictures, we see that the parabola here is symmetric about the y-axis. And if it's symmetric about the y-axis, we see that the graph is also even. This next one kind of has a couple hills and values. This is not symmetric at all. And if it's not symmetric, it is neither even nor odd. And this last one is symmetric about the origin. I see that a point down here, when I go straight through the origin, I get a different point. When I look at this particular point, go straight through, we end up with the point opposite when going through the origin. And if it's symmetric about the origin, we know that this is an odd function. Heading over to slide 3, the function behavior on a specific interval. Suppose f is a function defined on a specific interval. We say that f is increasing on the interval if when I evaluate at f of a and f of b, we result f of a is less than f of b for those real numbers on the interval. Similarly, it is decreasing if f of a is larger than f of b, and it's constant if f of a is equivalent to f of b. and it's staying flat. So if it's increasing, we can say that it's going uphill. When we are moving left to right, we're always moving forward. So regardless of which situation, if we're moving uphill, going from left to right, we are increasing. When going from left to right, we are decreasing. If we are going downhill, or if we are staying flat by going left to right, we are staying constant. So let's look at the picture below. When I'm looking at the domain, let's assume that even though we don't see it, let's assume that these continue going left and right forever and ever. Since it's going up and down forever and ever, we're always moving forward. Our domain is negative infinity to positive infinity. So when I'm coming from my x-axis here, moving left to right, I am coming from negative infinity, and I am going to continue on all the way to positive infinity. My range is also the same. So my range, if I'm starting from down here, because I'm going down into the left forever and ever, my range is also from negative infinity. And because my arrow is going up into the right forever and ever, my range is going to go to positive infinity. So let's talk about increasing and decreasing. So my graph is starting to increase because I'm going uphill again, working my way left to right. We are increasing all the way until we reach this point here. So I'm increasing from negative infinity looking at the x-axis, and I'm increasing all the way until the value of 1. And when I am representing increasing and decreasing, our values are always open. All right, then I hit the value of the x-axis at 1, and now I'm going to decrease. Now I'm decreasing, and then I hit this little valley here at the value of 3, and then I'm going to be increasing again. So I am decreasing from 1 to 3. At 3, then, I am increasing all the way until I reach the top of the hill here. So I've already increased a little bit. So in order to be able to continue increasing, we want to union another place where we're increasing. And we are increasing starting at the x value of 3, moving until we reach the x value of 5. In which case now I'm going to decrease because I'm going downhill all the way until I hit the x value of 9. So union, we start at 5 and we go to positive 9. And now we are constant, right? We are constant here. We are constant until this x value. So we are constant from 9 to 12 on the x-axis. And then we increase again. So I'm going to union my increase starting at 12, and we'll continue increasing until infinity. And that tells the story of our increasing and decreasing location. I also want to say that we should mention the zeros. I know it doesn't ask us, but just so we can look at them. There are 3 of them. We cross the x-axis here, here, and here. I don't know those exact values, but I do know that there are 3 solutions. 3 intercepts, if you will. Let's look at the next example then. The next example. Notice here on this particular graph that our graph starts here, it comes up, comes down, it's constant, and then it comes up till here. So we don't have any arrows. So our domain and range don't come from infinity. There's some stopping and starting points. So when I'm looking at my domain, the furthest left my graph is at -4, and it's a solid point here. So my domain goes from -4 all the way until this point here at my x value of 6, and 6 is included because it was a solid point. Now looking at my range, the lowest value of my graph is at -8, and our point, there is a point there, so the smallest value is -8, and our highest value is up here at 5.5, where again it is a solid point, so we are at 5.5. Now let's talk about increasing and decreasing. So working our way left to right, from -4 all the way up until this point, we are increasing. So we are increasing from the point of our x value from -4 all the way till -2. Then we make a corner and we decrease all the way down until we reach this point here. So we decrease then from -2 all the way to +3. We turn the corner and we increase until the point for -6. So I need to union from 3 to 4, excuse me, from that single point from 3 to 4. We remain constant, again for a single value, we remain constant from 4 to 5. And then we head and we are increasing from 5 to 6. So I need to union, I'm just going to draw an arrow here. We need to union onto that from 5 to 6. Now, along those dips and valleys and high points, we have what's called minimums and maximums. We have minimums and maximums. We have what's also called local or relative minimums and local or relative maximums. We also have what's called absolute minimums and absolute maximums. So if it is the farthest lowest point of the graph, it doesn't get any lower, we call that an absolute minimum. It also could be known as a local minimum as well, or a relative. So notice that local and relative are used one and the same, so the vocabulary is the same. Also notice that a local relative maximum or minimum can also be a global or absolute maximum or minimum. So this absolute minimum, also absolute's the same as global, so two different vocabulary words. This is also a local or relative minimum. Okay, so notice point P and point T are relative minimums. They could also be known as local for vocabulary terms. But the one that is the farthest, the lowest point, is known as the global or absolute minimum. However, point Q and S are maximums because they are hills rather than a valley. They are hills in this particular graph, but this particular graph does not have a global or absolute maximum because we can assume that these endpoints continue to go forever and ever. So it is possible to not have an absolute or global maximum. Also, endpoints of a function are not allowed to be local or global max or mins. Let's take a look at this graph here. We have ourselves 1, 2, 3 local maximums, or local is the same as relative maximums. And this very high point also is a global because it is the absolute highest. the same time, we have two local minimums or relative minimums for other vocabulary. Keep in mind, because noticing our arrows are going down forever and ever, we're not going to have a global minimum because our graph can always get smaller or get lower. How many local or relative minimums were there? We said that there were 2 of them. How many local or relative maximums? 1, 2, 3. Where one of those maximums just so happened to be the global maximum. And how many global or absolute minimums are there? And we said none. And notice, because our range goes from negative infinity all the way to positive 3 on the y-axis, so we always can get smaller. We'll always have another minimum. So there's never going to be an absolute minimum. We always can get smaller. And our last example, just grabbing another one, kind of putting all of the things together using a graph itself. I also have the picture here from Desmos, so I graphed f of x is equal to the opposite of x to the 5th plus 2x cubed minus x over x for us to take a look at. So let's look at the domain. We can assume that our graph is going left and right here forever and ever and down. So it's very slowly moving left and very slowly moving right, but it will forever and ever do that. So our range, our domain is from negative infinity to positive infinity. However, our range, as we come up from negative infinity, we are going to reach these 2 points here, and we're not going to go higher than that value. We're not going to go higher than the y value of 0. So our range starts at negative infinity, and the highest point that we get that is included, because there are 2 points there, is 0. Determine f of 2. So determining f of 2 isn't terrible. We can substitute into our equation what is f of 2. So the opposite of 2 to the 5th plus 2 times 5 cubed. 2 times 2 cubed minus 2 all over 2. This gives us negative 32, since 2 to the 5th is 32 times the negative out front. 2 cubed is 8 times 2 is 16, minus 2 over 2. Simplifies to negative 18 over 2, which is negative 9. So f of 2 is negative 9. List the x-intercepts, if any. We just talked about those x-intercepts, and I'm really grateful for Desmos that it usually has a gray dot that we can click on to ensure that we get those values to be exact. And in this particular case, these x values were nice whole numbers, so those values are negative 1, 0, and 1, 0. Where does our graph cross the y-axis? The same is true here. Desmos allows us to click the graph and identify those important pieces. So 0, negative 1. Further, we know that x-intercepts and real zeros mean the same thing. So this is trying to trick us with vocabulary. All right, now we're looking for where are we increasing and where are we decreasing. So starting from left to right, so from negative infinity to the x value of negative 1, I am increasing. Then I hit that x-intercept, and then I'm going to be decreasing until I hit that y-intercept. I'm decreasing then from -1 to 0. So these are the x values that I'm looking at, the x value. Then I hit the turning point of the y-intercept, which allows me then to kind of bounce up. Now I'm increasing again. So I'm increasing from the x value of 0 to +1. I hit that x-intercept, and now I'm decreasing, unioning. I'm decreasing from the x value of 1 to infinity. So again, when I'm looking for intervals of increasing or decreasing, I'm looking at the x-axis. I'm using the x values to determine where I'm increasing and how to label for the decreasing. What are the local maximums? Well, we've got two local maximums that also happen to be the x-intercepts. We do have a local minimum. This local minimum happens to be the y-intercept, and that's not always going to be the case. We have two absolute maximums. These are the absolute highest points of our graph, and they are equivalently the same height. So both of them get to be listed as the absolute maximum. So -1, 0. So these x-intercepts are really helpful for us today. Is there an absolute minimum? Well, no, there is not an absolute minimum because our range goes from -infinity to 0. So there will always be a smaller value that is smaller or more minimum. So there are none. And does this appear to be even, odd, or neither? It appears as if our graph reflects over the y-axis. And going back to the front, the second note page, I should say, if it is symmetric about the y-axis, we say that this is even. So it appears to be even because it appears to be symmetric about the y-axis. Please definitely utilize a graphing tool to help you with this lesson so that you can get a really good visual picture to help with the vocabulary.